Hey everyone, and welcome back. This is BackdoorCTF 2023, hosted by InfoSec IITR. Overall, pretty fun CTF. I'm going to be covering 5 of the 6 Pwn challenges, and with that, let's get started. The first challenge is Pwn Baby Formatter by Pochita. It says, just another format string challenge. Aren't they too easy these days? We're given a download file and a netcat port. Make sure you use the download file, included libc, and the downloads here didn't include libc for some reason. So as the problem says, it's a format string sort of challenge. All the protections are on for this binary, but we're going to be given 2 leaks right at the start, a libc leak and a stack leak, and then we have a repeated call to printf. So this is the vulnerable function. We're presented a menu, and we can just call this function as many times as we want. Every time it takes some input, and then it'll eventually do a printf. There's this filter function, which will filter out some of the characters. So we can't use %p, u, d, come on, or x. But we already have the leaks, so we don't really need this, but this is the setup for the next challenge, or the next 2 challenges. Yeah, that's pretty much it. The solution for this one, there's probably multiple solutions. At first, you would think it's a 1 gadget. Maybe 1 gadget would work, but I couldn't get it to work, so instead I ended up just writing a full ROP payload onto the stack. And so what we're going to be doing is we're just going to be calling this vuln function over multiple times, and we know where the stack is thanks to our leak. And we're just going to write out a ROP payload, 8 byte by 8 byte by 8 byte. And then when we return from the main function, where's main, we can specify exit. And so when we return, our ROP payload will be executed. And I think our ROP payload is just jumping to libc and calling a system bin shell. So really not too bad of a challenge. To see what the solve script looks like, this is all standard Pwn tool stuff, nothing too exciting. It's very useful to use pwninit on all of these challenges. I think some of the challenges linked to a local libc in the same directory, but it's still just a good idea to use pwninit. If you've never used it before, I'll just show how it works. Let's do challenge. I removed the challenge patch, so you just do pwninit. Oh, and let me remove core. You just call opt pwninit, and it pretty much just does everything for you. It'll find the binary, it'll find a local libc, and it'll find the linker. And yeah, this way that your challenge patched version is going to be using the libc in your local directory, and you can test that by running LDD. So the LDD of the challenge, we can see it's going to be using the libc that's here. This is my system libc, but if we run it on the patch one, we can see it's using the local version right here. So that way we're sure we're using the same libc as the remote system. Cool. Anyways, going back to the solve script. So we're using the patch one with the correct libc, setting up the process. We're calling to the remote. Let's just run it real quick. GDB challenge patched. If we run it, like I said, we get those 2 leaks. So if you do accept you are noob, here is the leak to the stack, and here's the libc. So at this point, you can cancel, and you can take those leaks and copy where they go. So if we look at the stack frames, we can see main is here. And so you can subtract with whatever the leak is, where whatever main is, or return is on the stack. And from there, actually, we can just do that real quick. Copy, let's do break. We'll continue. So main is here, and we look for the return address. I usually look for this address right here. So we're looking for CD90 on the stack somewhere. We can see it's right here. So the leak is already up there, but it's going to print out an address. And this is the stack address that has the return address because it is this address. And then I just do usually a print, whatever that value was up there. Maybe we can scroll up. We can. Except we are noob. Where is it? This one? Yeah, that's the stack one. Print. Minus, and then we're going to subtract this address. So this is how far it is. So it is 56 bytes away. So if we look at the solve script, oh, I put it in hex. Oops. Let's just print x56. We can see it is 0x38, and we can see it is 0x38. So the stack leak we're given plus 0x38 bytes is where the return address on the stack is. We're also given a leak to libc, and it's just the fgets function. And so we just subtract it since we have the same version of libc. So we take our leaks, subtract fgets, and now we have the base of libc and where the return address is on the stack. Like I said, I tried doing a 1 gadget at this point, but it just wasn't working. We need the registers to be in a specific place. So instead of just jumping to a 1 gadget, I'm just going to write out a full ROP chain. So we do ROP. Pwn tools does all the heavy lifting for us for both this part and the next part. We say we're looking for, first we have to do a ret gadget. So at first you don't do this. And when you execute your ROP gadget, you'll see something about some instruction that requires 16-bit alignment. It'll fail. I forget the instruction name. Maybe actually I'll leave it like this, and we can take a look. Get rid of this. Then we'll do pwn.gdb. We'll see something about alignment, and so then you add this extra return statement, And so that way on the stack will move back or down an extra 8 bytes. And so that way the stack address ends in a 0. And so specific instructions that are 16 or 16-bit align will work correctly. But yeah, we're going to have it call system. Pwn tools is going to do everything for us. It's amazing. So it's going to find the address of system. It's going to find a pop RDI and find the location of bin shell within libc. So it's going to be a pop RDI, that address, and then the call to libc. And we construct the payload. From there, we're going to be using the printf exploit to write the payload onto the stack. So if we look at the stack right now, there's just one return address here. So when this function calls return, it's going to pop this value off and start executing it. We're going to use printf and start filling in our exploit over all of these. So we're going to put a gadget here. It's going to return, then it's going to execute the next gadget, then it's going to return, it's going to execute the next gadget. Technically, since we're doing a pop RDI, it's going to be pop RDI. And then the next thing on here is going to be whatever we want to put into RDI, which will be our bin shell address. And then after here will be system. To write it out, we could construct the printf payloads by ourselves, or we can have Pwn tools do it for us because it's absolutely amazing. So that's what I ended up doing. So I'm enumerating over the payload. So for each byte in the payload, I'm going to do a printf. I'm going to specify what I want it to write. So at the return address plus the index, write the character in our payload. And then you tell Pwn tools to do it for you. So you say Pwn tools, build the format string payload. I'll talk about how to calculate this offset in a second. With these writes, like I said, the one we just specified, the return address and the character, and a write size of a byte. And that's pretty much it. You have to specify this offset thing. This is so Pwn tools knows how far your positional argument is on the stack. To see what this looks like, if we do run, then we'll do 1, 2, 3, 4, 5, 6, 7, 8, %C, 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 %C. And we'll just count to see when our first A occurs. So it is not the first one, the second one, the third one, the fourth one, the fifth one, but the sixth one. So positional argument 6 is where our payload starts. And you can also test this by doing try it again. 1, 2, 3, 4, 5, 6, 7, 8. And then let's do period percent $6 $C, the sixth argument, and we can say we get out an A. So if we were to put an address here and then do a %N, the %N would work on this address as long as we do a $6 sign. So that's what that offset thing is about. But anyways, back to our payload. So it's just going to write out the payload byte by byte. And when it's all done, I guess we could actually just leave the GDB here and run it. So let's do make Ubuntu, Python 3, tmux, Python 3 solve. Finish, 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 finish. Okay, so at this point we're going to send, we're right here, we're going to send the 3 over to GDB. And so this is the command, to the program, and this is the command to exit. So if we do, we're over here right now, executing this move instruction. If we step forward a bunch, eventually we'll hit this leave return. So normally it would return to libc, but we overwrote our payload using a bunch of payloads like this. This is the one that format string created, a %7 $LLN. So it's writing a single byte. You can do, I think, either LLN or HHN, but it's writing a single byte at this address. And it's using %7 instead of %6, at this address right here. But if you remember, we were doing %6, which is the first one. So then the next one would be the $7 sign. But anyways, so we're right here. Like I said, the first gadget is going to be a pop RDI. And so it's going to pop a bin shell off the stack. So we can do a single instruction. Now we're at this pop RDI. If we look at the next thing that's on the stack, which is right here, we can see it's bin shell and address to bin shell. So we'll pop that off, put that into RDI, and then it jumps into system. And so now we're in system. We can just continue and it'll start running. Like that issue I said we were going to get. So some of the instructions, specifically one that looks like this, if it involves the XMMM registers, these are, RSP needs to be 16-bit align, which basically means that this needs to be a 0. So we can see the RSP register right at the top. Since it ends at an 8, it's not going to work. But if it ends in a 0, it will work. So what we're going to do is we're just going to put an extra return statement into our payload. So that way the stack just jumps down an extra 8 bytes. And this instruction will work and system will successfully call. So let's put it all back the way it was. And let's call the remote and see if it still works. And we have shell. So count out the flag. It says format strings are too easy. So fun. The next challenge is Pwn Master Formatter, also by Pochita. It's a similar challenge as Baby Formatter, but with some added constraints, given a download file and a natcat port. Again, the download file has libc, and libc was not listed here, so make sure you use the download file. So this challenge is pretty much the same as last time, except there's two constraints, but neither of the constraints work, so it is actually the same challenge as last time. The first constraint, if we go to the main function, unfortunately this time it's stripped, but it's pretty easy to read. We can only call the vulnerable function twice, or we're only supposed to be able to call the vulnerable function twice. That's what this is. So this is, we'll just call it counter. If counter is less than 2, we can call this is the vuln function. Otherwise, it would be run out. But you might notice that there's nothing incrementing count. So since count is never incremented, we can just call it as many times as we want. So there is no actual constraint there. The other constraint, we actually saw it last time. This is the filtering function that's being used. This doesn't actually filter enough to not get a leak. Sorry, let me back up. In this challenge, they only give us a libc leak. So we only get, last time we got both libc and a stack leak. This time we only get a libc leak. But printf, it's very easy to leak values. And to prevent that, they implemented this filter function, but this filter function doesn't actually work. Like there's way more values that you can use to leak values off the stack. I think in my code, I'm going to use an uppercase X. So we can still just easily get a stack leak. And yeah, because of those bypasses, this was the exact same challenge as last time. If we look at the solve script, all standard stuff. First, we're going to grab the libc leak, same as last time. Like I said, we don't get a stack leak. To get the stack leak, this is the code I used to just find a stack leak that looked interesting. I just iterate a whole bunch of times. I send an I, so for I group by threes, a $, and then L capital X, so it's a long hex. And I just see what prints out. Eventually, I'm just looking for a value that looks somewhat interesting, and it looks like, relatively low. And because we want a value that's kind of near our stack frame. Eventually, I find %12 $LX is actually only 8 bytes away from the return address, so I just use this value. So now we have a stack leak. We calculate the return address. We have the libc base, and so this code is pretty much copy-paste from last time. We're going to generate the ROT payload using Pwn tools. Very cool. And then we're going to use Pwn tools again, and they're going to generate the format string payload, the exact same as last time. And when we're done, we just click 3 to exit, and it should execute. So we can run it. You can see I already ran it right there, but run it again, Python 3, solve.py. Because of the filtering, the script will fail a lot. So like if your address has like an underscore X in it, for example, it'll fail. But here we go. We got shell, and we count out the flag. It says flag writing PLT with format string is fun. So the intended solution was to use PLT. If we take a quick look though, check sec file chow. Full railrow is enabled, but I think they're referring to writing PLT in libc, which I'll talk about in the next challenge. The next challenge is Pwn Master Formatter v2, also by Pochita. It says this time no leaks, hopefully. We're given a download file and a netcat port. So same challenge as the last couple of times, except they fixed 2 of the issues. The first fix is they now filter a whole bunch of characters. And this is pretty much all of the printf characters, except they're still missing one. So you can still cheese it, which is what I ended up doing. And there was also, in the main function, they now correctly increment the counter so that we can only call printf twice. So based off of the hint last time, it said something about overwriting PLT entries. If we did the check sec on the binary, we would have saw both last time and this time, it's run with full railrow. So we're not going to be overwriting the PLT of the binary. But if we look at libc, it is only partially railrow. So we could overwrite global offset table entries within libc. So I spent most of today trying to get this to work, and I'll kind of show what that looks like, but I couldn't get it to work. I just couldn't put a one gadget in there. If someone else figured out, I'm very excited to see that write-up. It was just very tricky. So I ended up resorting to cheesing it, but I'll kind of show, I think, what is the correct intended solution, and maybe I'm just missing something silly. To see what the PLT looks like, what we can do is, let's run it, gdb, chow patched. Let's break on string dupe, and then let's run it. Another one, we'll do hi. And so now we're in the string dupe function. I need to make this just a little bit smaller because we need to be able to see the function we're executing. What you can do is just kind of step forward until you find something that looks like code for a PLT. And we can see we already found it. It's this jump to a offset table. So we can print it out, print RIP plus this, and we get this entry. So we're in a global offset table within, if we do a VM map on this, within libc. And so this is both readable, writable at a table. So I think that the challenge was we were supposed to overwrite this value here, with a one gadget. Like I said, I tried that and I just couldn't get it to work. None of the registers would align up such that I could do a one gadget. I tried going up and down the one gadget, looking for things nearby to maybe like change the register a little bit. I tried calling other functions so that the register would be in a better state. I tried something called Anger Gadget, which looks really interesting. Some repo where they're running Anger over libc. Tried to get that working. I was running into a couple of issues getting it working, but I think I kind of got it working, and it still wasn't returning anything useful. So again, I'm not really sure. I'm very curious to see how it works, how overriding these PLT entries was supposed to work with the one gadget. I tried jumping directly to a system. In RSI, you can have the string, and so maybe you could try calling like a POSIX spawn, which takes bin shell as the RSI argument. Instead of RDI, but couldn't get that to work either. Like I said, I spent most of today trying to get this to work and I couldn't. So instead I ended up cheesing it. The way I cheesed it was in the filter function, they're not checking for %s. So we can leak stack values doing that. So %s is a little bit different than like %p. %p will print out the value on the stack. %s takes that address and then prints out the value at that address. There's like a layer of indirection. So what we can do in our solution, let's go here, solve. So what we can do with the %s, this is the code I was using for looking for interesting %s targets, is I just start doing %s across the stack until we find a entry on the stack that also points to the stack. And when we do a %s on it, it'll print out that address. Frustratingly, there is one that worked for me locally very well. That was very close to the stack frames. And so I was able to just get a stack leak like that. It did not work on remote. It was like the only value that didn't show up on remote for some reason. So I think it was like %18 or 23 or something like that. It would just perfectly print out a good stack address, and I had my stack leak and it was good to go. But yeah, it didn't work on remote for some reason. It printed out like nil, I think. So I ended up skipping that. So instead I had to find a different stack leak, and the stack leak I ended up using is, I think, libc stores like the environment variables or something within the libc library, or sorry, within like the libc memory section. And so you just have to find one of those. So we run it, we copy out the first 4 bytes. We'll do search 4 bytes, this within libc. We get 3 entries. So we can copy this one out and it's gonna be offset by 2. So let's examine the address here. +2, -2. This looks good. So -2. So at this address in libc, it has an address to the stack. So we can examine what this is. There's no symbol for it, so I'm not really sure what it is. I think libc stores like the environment variables and stuff, so I'm guessing that's what it is. But anyways, we know what the base of libc is. We can calculate how far away this is from the base of libc, and then we can use a printf exploit to print out this specific string. And so it's going to then point to, it is a pointer to a variable that contains a stack address, which is this. And then we'll get our stack leak like that. A little bit of roundabout way to get a stack leak, but it works. And then once we have the stack leak doing that, I can show what I ended up doing. It ends up, this is being the offset. Like, so we have to do a -2 just because we're searching for 4 bytes. Then we're to grab that stack leak out. We're just going to do a $7$ $s ... So this is 8 bytes. And then with that specific address. And so that way it'll leak, whatever value is at that address, what happens to be a libc address. And then from there, we can calculate the base to our frame pointer. And specifically, we want to figure out the address to our counter and the address to the return address. We need the return address because we're going to write more ROP code back onto the stack like every other time. And we want the counter address because we're going to cheese the counter so that we can do unlimited printfs. So to cheese the counter, it's doing a signed comparison. So what we're going to do is convert that number into a negative number. And to do that, we just have to set the very top bit, or the MS bit, most significant bit, to a 1. And so that way it treats it as a large minus number, negative number. And so we can do as many writes because I think it's just checking to see that it's not greater than 2. And a large negative number obviously is not greater than 2. So do that exploit. I just did it by hand, so we're going to write 128, so it's just the high bit is set. And then we're going to write the byte at the 8th positional argument. So if we remember, by default, offset was 6. You can kind of see it right here. So this is, offset 1. So this will be 6, and then 7, and then whatever value is in this address, it's going to write, this single byte. And so we're taking the counter address plus 3. So, this is some specific variable. Oh, the counter variable is also just a 4-byte integer. So we're just going to go to the high byte, and we're just going to set the very high bit to a 1. And again, at that point, it's a negative number. So we can do as many writes as we want, and we have the return address, and we're going to do the same thing we did the last 2 times. We're just going to write out a ROT payload, send the payload, and then exit. So we can give it a run, Python 3. Because there's so many checks in this, the script fails a lot. So you just, am I doing a GDB? GDB. No, but I'm also not doing remote. So you do have to run this quite a bit. I'm not sure how it was working before, but I guess I was missing this receive until. For some reason, I don't know how that was working before. Maybe I accidentally deleted it. But anyways, it's working now, so it worked locally. Let's try running it on remote. Python 3, solve. Looks like we had a bad byte. And we have shell. So count out the flag. It says flag, a format string without leak. So not the intended solution, but fun. The next Pwn challenge was Pwn Consolidator by Pochita. It says, well, libc 231 is easy, isn't it? We're given a download file and a netcat port. So another cheese solution, based off of the flag, we're supposed to be doing a House of Muni attack, I believe. I didn't do that. I ended up, I guess, cheesing it. The idea was that you weren't supposed to have a leak to libc, but it's really not too hard to get a leak to libc. But anyways, so for this challenge, very traditional sort of heap challenge, we're given a bunch of options. So we can add chunks and we get to specify the size. The bug, the intentional bug for this challenge was we can change the size of one of the chunks. We can delete chunks, we can edit chunks, and we can exit. You can see there's like no print option though. And so I think that's like, where we're not supposed to have a leak. And so then, we need to do one of those leakless sort of exploits. So for this challenge, we're using 231. So we're mostly just going to be playing on the T-cache. And the idea is we're going to create a chunk, and then we're going to create another 2 chunks. You could probably do it with just 1 chunk, but we're going to create 2 other chunks. Then we're going to edit the size of the chunk that's all the way at the top. I think initially I give it a size of like OX20. We would change its size to OX200. So that way we can modify the 2 chunks below. Then we free those bottom 2 chunks. And since we have that OX200 byte chunk, we can modify the pointers on those chunks, and we'll modify them so that they point to the global offset table for the main elf, which was thankfully writable because RORO wasn't enabled. And so we're going to overwrite the entry for free. Instead of having it call free, it's going to call printf. So in the future, when we free a chunk, really it's just going to call printf on that chunk. And so we're going to create a chunk, and we're just going to do a printf sort of exploit where we leak a bunch of values. From there, we're going to get a leak to libc. And then from there, we're going to edit that chunk again. Instead of having the free go to printf, it's going to go to system. So then we create another chunk, and we have it fill it with bin shell. And when we free it, it'll do system bin shell. So really not too bad of a challenge. This is what the exploit code looks like. So all standard Pwn tool stuff. These are all the different functions: add chunk, change chunk, delete chunk, edit chunk. Like I said, we create a chunk at the top. This is going to be our big chunk, and we give it index 0. Then we create 2 other chunks and we free them. You could probably do it with just 1 chunk, but I like being able to see the pointers. And we can make as many chunks as we want, so it doesn't really matter. Then we're going to change the size of that top chunk. So originally it was size 20, now it's size 200. So this is definitely going to overlap with those chunks. And so since we freed the chunk, it's on the T-cache. The T-cache has those pointers. So we're going to edit the big chunk, and we're going to change the size. So the size is already OX31, so we're going to leave that the same. But normally it would print the next pointer would print to the next chunk, but we're going to overwrite it, and we're going to say, instead of pointing to the next chunk, I want you to point to the global offset table entry. And this was one of the global offset table entries. Really, we could just hard code the value, but I saw this and I added 8 for some reason. So whatever this is, and I think I picked this one specifically because when you create chunks, sometimes it nulls out bytes, and so you need to null out something you're allowed to null out. So Then when we add 2 chunks, this will add a chunk, and then it sets the pointer to the next chunk to be in the global offset table. So then when we create the following chunk, this chunk actually exists in the global offset table. And so we can start writing to this chunk. And so I'm just going to write printf a whole bunch of times, and this will overwrite the global offset table entry for free. And so instead of free, it's now printf. Then from there, we're going to create a new chunk, and we're going to give the chunk contents to be equal to $33$P. And I found this just because just if you leak out a bunch of values, eventually you find a value that looks like a libc address, and $33 ended up being that. To a p receive, I think I just needed to clear out a bunch of stuff. Then we delete that chunk. So instead of when we call free, it now calls printf. And so we'll get that leak. So whatever this value is, we'll read it out. In GDB, you just calculate where that is to the offset of libc, the base of libc. And so now we have our libc leak. Once we know where libc is, we can again edit that big chunk. Sorry, we can edit the chunk that is in the global offset table. And so we're going to do 3 printfs. I forget, I'm overwriting some entries. Instead of like having it clobbered, I just print out whatever it was supposed to be calling. And then I have it call system. So this was the entry for free. And so instead of calling free, it calls system. So then we create another chunk. We create the chunk contents to be equal to bin shell. And then when we free it, it calls system now, and we get shell. See what this looks like. Python 3, solve.py. Do ls, and there's the flag. Cool. It says flag steal libc with Muni. So yeah, I think there's a exploit. It's called House of Muni. House of Muni. You can see I already Googled it. There's a good blog post on it. This one. This is like a leakless technique using Mune mapping. Thankfully, we didn't have to do that. There was an easy way to cheese it, but fun challenge. The last pwn challenge I was able to solve is Pwn Pizzeria by Pegasus. It says, welcome to our land pizzeria. We serve our customers the best and the most delicious pizza in the world. Go check it out. Given a download file and netcat port. So this is another heap challenge. The idea is that you're creating pizza, but all the pizza toppings are different heap chunks, and somehow we have to get shell. There were 2 intentional bugs in this challenge. The first one was that we can view the contents of a free chunk. And so we can use that to get our leaks to the heap and our leaks to libc. The next one was a double free. So you can free the same chunk multiple times. And yeah, using those 2 things, we can get shell. The libc version was 235. So what I ended up doing for this challenge was first, I get leaks to both the heap and libc. We can get the heap leak using the tcache bin, and we can get a leak to libc using an unsorted bin. So we fill up the tcache with a large enough chunk, and it goes on the unsorted bin. And the unsorted bin, I think the backwards pointer points into the libc arena. So leaking that, we have libc. Then from there, we have to do a double free. I kind of did like a House of Bot Cake-ish sort of thing. Maybe it's considered House of Bot Cake. I don't really know House of Bot Cake, but I don't think you can just do like free ABA to get a double free on the tcache in 235, or at least I tried and it didn't work. I didn't look too much into it. But if you if you fill up the tcache, things will go onto the fast bin, and you can kind of do a double free on the fast bin. The chunks end up getting consolidated back onto the tcache bin, but it still lets me free a chunk I've already freed again. I freed it on the fast bin, and then it gets moved into the tcache, and then I free it again, and for some reason that doesn't trigger the double free alarm. Not really sure why, but it worked. So once we have a double free, obviously we can create a chunk, and then modify its metadata so that it points somewhere interesting, and then after we free another 2 chunks, we create a chunk at that arbitrary location, and so we can get chunks at arbitrary locations. For actually then doing some exploitation, similar to what we did in the previous challenge, I tried to get 1 gadgets to work. I couldn't get any 1 gadget to work anywhere. I got very frustrated, so I ended up just leaking a stack value, very similar to a previous one of the printf challenges we did. So I leaked like some argv value or something. I forget what I leaked, but something in libc has a leak to, there's a symbol in libc that contains a stack address, and it is libc argv. So I ended up leaking this. Once we have a stack address, stack leak, I figure out where the return address is. I think I do find the return address when a call to the read function is made, because I don't think this code actually calls return. It calls exit at the end. But I found out that when you call read, the return address is here, and it's there every time. So I just write my payload during the read, and then as read is returning, this ROT payload gets executed. And this is just the standard ROT payload I used. So To see what this actually looks like, there's some other stuff like you're supposed to, instead of accessing things by indexes, you have to access them by toppings. One thing that was frustrating though is on the customize call, you had to be a little bit careful about how you did it because it's just like, I think it was like an fgets and the fgets was like 1 byte too small or something like that. And so sometimes it would hang. So you have to do either a p send after or a p send to line after. This new line would get things kind of confusing. It was a little bit tricky to debug. If anyone else is running into an issue, it's specifically on the double cheese. So if you're not using double cheese, I should have just used a different one just because double cheese is so long. It kind of got messed up. But anyways, you also needed this timeout because this is what we're going to use to actually do the exploit. And this doesn't always return if you spawn a shell, or you can just call it manually. But a quick trick if this line won't be here because we've spawned a shell, you just use a timeout. Otherwise, it's just the rest of the functions, nothing too exciting. Like I said, first we're going to get those 2 leaks. We need a leak to the heap. The reason we need a heap leak is because it's 235, so they're using the smart linking in the T-cache. And so the T-caches, normally it's just a linked list that points to the next chunk. But all of these chunks, the pointers are mangled. So instead of just being an address, it's XORed with the base of the heap, shifted by a couple of bits, by like 12 bits or something like that. So we have to leak the base of the heap. And so that way we can construct these smart pointers so that, we can do the linked list. So we leak out the heap. And like I said, we're doing it relatively large. I think these are shifted left by either 3 or 8. I think by 3, so it's multiplied by 8. I forget, but these end up being pretty large chunks, and so they go in the unsorted bin instead of the fast bin or something like that. And we want the unsorted bin because, like I said, it has a backwards pointer that points into the arena, which is in libc, so we can get a libc leak. And so that's what we do. So in part of the verifying call, it's one of the menu options. It'll give you the response. So we free it, we get that backwards pointer, so we get the libc leak, and then we just subtract the values from vmmap within GDB, and we get the libc address. And then we do the same thing with these. We just verify toppings on those free chunks so we can get the base of the heap, and also one of the pointers just to see what it looks like. From there, at cleanup, I then re-malloc all those big chunks. I just don't like them in the bin list, just in case it tries to consolidate or do something weird. From here, we're going to be doing the double free. Like on earlier versions of libc, like on very old versions of libc, you can just double free something and it doesn't get mad. And then later you had to do like a free A, free B, free A. I think on 235, maybe I'm wrong, you can't do that anymore. But thankfully, if we fill up the T-cache, then chunks go into the fast bin. And like I said, I did like a ABA on the fast bin, but then at some point those get consolidated onto the T-cache. And then I can still free that T-cache entry and it works. Not too sure why. I think that it might be a house of bot cake. I just looked at the description of that. I've never done one and it seemed very similar. So maybe that's what it is. But however this worked, again, just going from the filling up the T-cache and then going onto the fast bin and freeing, I was able to get a double free. And then like I said, once we have a double free, we can modify the forward pointer so it points somewhere interesting so that as we malloc more chunks, we can create a chunk at an arbitrary place. That arbitrary place, like I said, was this libc address, specifically libc argv, and this contains a stack pointer, and we're trying to leak a stack. So we grab this. Oh, at some point, the heap leak base pointer had to increment by 1. I guess it's a different size for different bins. I wasn't too sure about that, but that was interesting. So we're going to modify our double free, and we're going to pass it the address where there is a stack leak. Like I said, it has that smart linking, so this is the target where we want it to point. We have to XOR it with the base of the heap. And then from there, we're going to allocate 2 chunks. And then the second chunk will be the actual chunk that is in libc at that, that libc stack leak value we wanted. So we're going to grab out that stack leak. From there, you just kind of play within, GDB, and you just look at the stacks, and eventually you can figure out where the address of the return address is based off of the offset of the stack leak. You can see I was playing with it for a bit, but eventually I found it. And so this return address is the place in the stack where the call to read will return. And read is the call that, we're going to exploit and write our ROP chain in. So on that return call, I'll place the ROP code, and this is the return address for that. Cool. So we need now, we have a arbitrary chunk in libc. Now we need to create that arbitrary chunk at that address, at the return address in the stack. So we do the exact same thing. We're going to do the double free, maybe a house of bot cake. I don't really know what it is. We do the double free, we fill up the T-cache, then we have 3 chunks on the fast bin. At some point they get consolidated back to a T-cache, but you can still free them again for some reason. So we get a double free. And at this point, we're going to create a chunk at the return address on the stack. So we create that. And so now toppings 8, like I said, you had to, instead of passing indexes, you had to pass the toppings, but it's basically an index. So now we have a chunk in the stack, and it's at the return address. And so now we can just write our wrap code. So I generate some wrap code and customize, and I place it. Oh, I think I had to do a slight offset, because if I put it right there, it clobbered something. Yeah, clobbered whatever function it was in. So if I just put it down a bit and then just put in a bunch of pwn cyclics, it didn't clobber anything until I needed it, and I could still write the ROP chain. So I'm guessing, yeah, I think I had to shift it down 64 bytes from where it originally was. So this is ret minus 64, and then I just did or minus OX 34 or 38, and then I just fill that up, and then I start my ROP chain. But yeah, it ends up working, and then we get shell. So Python 3, solve.py. This one definitely takes a second. Cool. Ls, and we have shell. So cat flag.text. It says flag, never have I ever had pineapple on pizza. So fun. Actually, before I go, I think the intended solution is probably something to do with RLP. Maybe this is like an exit handler or something. I'm not too sure, but it's really weird that RL and P are capitalized. Maybe that means something. I'm not too sure. Anyways, fun. And that is all the challenges I was able to solve. So thank you for hosting some fun chows. As a reminder, I'm still doing ctfwriteups.org. So at the end of a CTF, I'm just going to start compiling every write-up I can find, and I post it on this website. And people can vote for their favorite write-up, but really it's just a way to kind of consolidate all the write-ups that have been written so far, so that not everyone is, control Fing through Discord. Zero CTF was a little bit strange. Oh, I guess there hasn't been other CTFs. Let me go back. But if we look at like Hackapatoy, we can see all the write-ups for all the different functions or the challenges are here, in just like a nice sort of clean way. And anyone, as long as you're logged in, can add write-ups. And at the end of the week, a email is sent out with the top 5 rated write-ups for that week. So if you're interested, it's just ctfwriteups.org. But anyways, thanks for watching, and I'll see you at the next CTF. Cheers.